Welcome. In this session, we'll continue the discussion on this how to compute the this uh, complex power and real power of the elements. Okay, if we know the currents and voltages. All right. So let's suppose we have an example. All right. So we have an example here where two elements are connected in parallel. And these two elements are connected across the source. The voltage of this source is given, that's given as 120 at an angle of 0 degree volts, and this is the RMS value of the voltage. Okay, so RMS value was given, and Z1 is the impedance of this element, and Z2 is the impedance of this element. So we are given Z1 and Z2. Z1 is simply 60 at an angle of minus 30 degree, and Z2 is given as 40 at an angle of 45 degrees. Now what we have to do, we have to calculate the total power. Okay, we have to calculate the first part is we have to calculate the total apparent power. That is the first part of this problem. Second part we have to do is the real power. And the third part is the reactive power. Supplied by the source. Supplied by this source. Supplied by this 120 volt source. Supplied by this source. So this is the first part of the problem. Second part is, or the D part is, find the power factor seen by the source. So we have to also find the power factor seen by the source. At what power factor it's solved means what is the cosine of the angle of the phase difference between voltage and current. So how will you solve this problem? Now the first thing is we know the voltage across this source, but we don't know the current through this source. So if we know the current, we can multiply that by voltage. That will give us the apparent power, real power, and reactive power. So what do we need to find? We need to find the current. So let's mark the current. So let's suppose the current that is flowing here is I1. Let's suppose the current that's flowing is I2. And let's suppose the current that is total current is equal to I is equal to I1 plus I2. So let's solve this network. So to write the solution, we'll say I is simply given by I1 plus I2, right? Very simple. Using the KCL. At this point, I will be simply equal to I1 plus I2. So let's find what's I1 and I2. As you can see, the three elements are connected in parallel. So we know the voltage, we know the impedance, so we can get the current. So very simple, right? So I1 is simply given as, what's I1? I1 will be simply given as V divided by Z1, right? V is simply 120 at an angle of 0 degree divided by Z1 is, I think, 60 at an angle of minus 30 degree, at an angle of minus 30 degree. So simplifying this, this will be 120 divided by 60, that's 2, 0 minus 30, that will become plus 30. So it will be plus 30 degree. So the current flowing through the element 1 that is named as Z1 is 2 at an angle of 30 degrees. This is not 3 degrees, this is 30 degrees at an angle of 30 degrees in amperes, and this is the RMS value. Why is this RMS value? Because voltage is given in RMS. So if voltage is given in RMS, current will also be in RMS. Okay. Now this is the current, first current. Now current flowing through the second element that is given again V by Z2 because the voltage will remain same. So it will be 120 at an angle of 0 degree divided by, I think it is 40 at an angle of 45 degrees. So 40 at an angle of 40 degree will be simply 120 divided by 40 is 3 at an angle of, I think it is 10 degrees. Okay, so sorry about this. This is not 0 degrees. This is 10 degrees. So sorry about this. So this is 10 degrees. All right, this is not 0 degrees. So this is 10 degrees here. So this will be 10 minus 30. So it will be 40 degrees. So sorry about this. So this is 10 degrees. So 10 minus 35 is 10 minus 45 is 35. Again, it's amperes, and the value is in RMS. So this is the RMS value of the current. Okay. Now, what is the complex power absorbed by the impedances, means Z1 and Z2? Now we know the voltages, we know the currents, so we can get the complex power. Let's name them I1 and S1 and S2. So the complex powers absorbed by the elements. So complex powers absorbed by the elements Z1 and Z2. Absorbed by the elements we termed as Z1 and Z2. Let's say the power absorbed by the Z1 is S1, and it will be denoted by using the definition of the complex power. V term is I1 conjugate, right? V is the RMS value of the voltage across the element. I1 is the current flowing through the element, and we take the conjugate of that. So that will give us 120 degrees at an angle of 10 degree multiplied by I1, we got as 2 at an angle of 40 degrees. So 2 at an angle of 40 degrees. So multiplying these two, so it will be 2. So that is equal to 240. So 240 at an angle of minus. So how much was this? So this is plus 40. Okay. So this is plus 40. So how much is this? So this will be 50 degrees, right? So angle is add in multiplication, angle is add. So this is the complex power absorbed by the impedance Z. Okay. Now you can get the what is the real part, what is the average power absorbed by the element or consumed by the element, right? Because it has a real part as well as imaginary part. As you can see, this is complex, so that means this has an imaginary part as well as a real part. So that means the power can be expressed as cos 50 degrees plus J 240 sine 50 degrees. Please check the calculations one more time. Okay, please verify the calculations. So this comes out to be 207.85 minus plus J 100. I think I did somewhere wrong. It's my calculation. Okay. So this is minus. Yes, okay, here I did wrong. What did I do wrong? Because this should be minus. So this is what I did wrong. Okay. So this is wrong. Okay, because I have to take the conjugate of I1. I forgot to take the conjugate. So it will be 240 at an angle of minus 30 degrees. All right, you can check it. 10 minus 40 is minus 30 degrees because I have to take the conjugate of this current. This is plus 40. That means it will be minus 40. Okay, that's what I was thinking of, what I did wrong. Okay, so this is voltage amperes. Now we can express this in the rectangular form. So it will be 240 cos of minus 30 degrees plus J 240 sine of minus 30 degrees. Okay, now simplifying this will be 207.85 minus J 120 degrees. Okay, volt amperes. Okay, if you know the definition of what is this and what is this, you know this is the power absorbed or consumed by the resistance that is present in this part. So this is the power consumed or absorbed by that is the present in the by the resistance that is present in the first branch, that is a Z1, and this will be the power stored by the capacitor there. Why is this a capacitor there? Because Q you can see is negative. So you can see this is the power stored by the capacitor that is connected here. Okay, directly getting the meaning of this. What are the elements here? Okay, so this is the power absorbed by the resistance that is present there, and this is the power stored by the capacitor. Why? Because Q is negative. Right, it is P plus GQ because Q is negative, so you can say directly it is a capacitor there, capacitor load connected there. Now the complex power consumed by the S2, and this Z2 will be equal to V times I2 star. Why is V same? Because these elements are again connected in parallel, so voltage will remain same. We know the current, we can get the value. So V is 120 degrees, 120 at an angle of 10 degrees multiplied by how much was the current? Current is 3 at an angle of 35. So it will be 3 at an angle of plus 35. Why? Because we have to take the conjugate of that. So it will be plus 35. So how much is this? So this is 360 at an angle of 45 degrees. Why 45 plus 10 plus 40, 35 is 45 degrees. Okay. Please verify the calculations yourself. Okay. Please verify the calculations yourself. All right. So 360, we can express this in the electrical form. Cos of 45 degrees plus J 360 sine of 45 degrees. Please check, verify the calculations one more time. All right. So that means this is equal to, when you substitute the value of cos 45, you will get 254. So it will be 254.6 plus J 254 point. Why is the value of real part and imaginary part same? Because cos 45 is 1 by under root of 2, sine 45 is 1 by under root of 2. If you remember, the value of the sine and cos is same, volt ampere. So this is the complex power consumed by the element 2. All right. So that means this is the power dissipated by the resistor that is present here in this branch, and this is the complex power. This is the power stored by the element here that's present here. Now you can see Q is positive. You can say that means the second branch has inductive loading. Okay. So what will be the total power supplied by this source? Total power will be simply the total power consumed, complex power consumed by this and consumed by. Very simple, right? Intuitive answer. So the total power supplied by the source will be equal to the total power consumed by the elements. Elements are two parallel elements. So the total power consumed or supplied, let me write the supplied by the source. By source. Okay. Or you can say the power, total complex power. Okay. We are talking about complex power. Total complex power supplied by the source or total complex power consumed by the two elements. Okay, one and the same. The statement is one and the same. That means will be given by ST, that's equal to S1 plus S2. Now S1 is simply how much we got. S1 is 207.85 minus J 120 plus S2 is, I think, 254.6 plus J 254.6. Okay, so adding the two terms, we'll get 462.4 plus J 132.6 volt amperes, right? Because the unit of S is volt ampere. So what is the apparent power supplied by the source? So what is the apparent power supplied by the source? So apparent power, that is given by the magnitude of this ST is given by 462.4 square plus 132.6. Okay, so if you take this square, if you calculate it, you will get, I think this is 134 here. Please check the calculation. Okay, I think this is 134.6 here. Please check the calculation. So this will be 134.6. Please check the calculations yourself. So it will be 481.6 VA. So this is the volt apparent power supplied by the source or consumed by the two elements. Which elements? Z1 and Z2. Because the total power supplied is equal to total power consumed. All right. So the second part of the problem was, what is the total real power? Total real power means, what is the total real power means S1 and S2. How much is the real power supplied by the source. That will be the total real power absorbed by the two elements. Now the real power absorbed by the first element is this much, and the real power absorbed by the second element is this. So just simply take the into the sum. Okay. So the total real power, okay, is equal to, let's call it PT, will be equal to P1 plus P2. What's P1? P1 is the power, real power absorbed by the first element, okay, and P2 is the real power absorbed by the second element. So it is 207.85 plus 254.6. That comes out to be simply 462.6. You can check it is the real part of the total power. You can check it should be equal to the real part of the this, because the total real power absorbed by the two elements should be the total real power supplied by the source. Okay, so PT is simply P1 plus P2. Or this is simply the real part of the ST. Okay, all right. C that we needed to find is the total reactive power. So the total reactive power is QT, will be simply Q1 plus Q2. What's Q1? Q1 is the power absorbed by the first element, and Q2 is the power absorbed by the second element, I mean the reactive power. So this will be simply as minus 120 plus, how much is this? 134, I guess, not 134, 250, 254.6, 254.6. So this is simply as how much? 134.6 VAR, because the unit is volt ampere. So this is the total reactive power supplied by the source, or total reactive power absorbed by the two branches that are connected in parallel. So this is the total reactive power stored by these two elements, or you can say this is the total reactive power supplied by the source, because when the source supplies, elements get stored. Okay, so source has to supply. All right. Okay, so last point that we needed to find is the power factor. So power factor, that is denoted by PF, is equal to the, this means the power factor of the circuit or the power factor of the source divided by ST. So how much is this? PT is 462.4, I guess. How much is this? PT 4.4 divided by ST. ST is 481.6. 481.6. So the power factor of the load is 0.96, and it is lagging. Why is this lagging? Because you can see the apparent power has Q2, means the total apparent power, or total apparent power, or the total this total reactive power of the circuit is plus. So it is a lagging flow, right? Because inductor has Q positive. All right. Okay. So this is the answer. All right. So now see what I did here. I calculated the this complex power consumed by this element and this element. Because the complex power must come from the source, I said whatever is consumed by these two must be supplied by the source. That's what I used. Okay, but we can use also the this element approach. Means if I know the voltage and current of this element, we can also do that. Now, for that I need to find what's the voltage across the element. I know already the voltage across, but I don't know the current flowing through this element, that's I. So if I get I, which is equal to I1 plus I2, let me verify this, the results that I obtained using these complex powers, right? So let's do a check here. So let's do a check. What we'll do a check. So if I use the current approach, so current is equal to I1 plus I2. Now what's I1? If I remember it correctly, it is 2 at an angle of 40 degree. We are given the currents in the polar power of 3 at an angle of minus 35 degree. So to add these, you must convert back them in the rectangle path, because that will be easy. So it will be 2 cosine of 40 degrees plus J 2 sine 40 degrees plus 3 cosine of minus 35 degrees plus j 3 sine minus 35 degrees. So simplifying this, you will get this as 1.532. Please check the calculations one more time. 846 plus 3 cos minus 35 is, I guess, 2.457. Please check the calculations. Minus j, I think this will be minus 1.72. Please check the verify the calculations. So it comes out to be 4 minus j 0.435, which is equal to, in polar form, 4.024 at an angle of minus 6.21. All right. So this is the current, okay, flowing through this source. So that means complex power is simply given by voltage multiplied by the current phasor. So what will be the power supplied by the source? So power supplied by the source will be simply, complex power, okay? Complex power supplied by the source simply equal to V times I phasor, okay? V is simply 120 degree at an angle of 10 multiplied by I phasor. I phasor is 4.024 because this is the total current flow at an angle of plus 6.21. Okay, why? Because I have to take the this conjugate of this. So it will be simply 482.88. Please check the calculations. This will be 16.21. 10 plus 6.21 is 16. Now you can check what was ST here. It is 481 point. Okay, this is 481. This is not 482. This is 481. You can check the calculations. Okay, so this is 481.88 something. Okay, please check the calculations yourself. So it is the same quantity. Or you can express it in terms of this. So it will be 463 plus J times 135 volt amperes. Now you can check, verify the calculations that we did using the power complex power absorbed by the elements, and you can check the calculations are accurate. Here we come, the value was 462.4. Here we got 463, very close because we use approximations. That's why there is a minute error. Okay, and reactive power was, RQ was equal to 135. Here the reactive power is 134.6 because we used the approximation of the equations. So in other words, we got the same answer. So earlier, what I did, I calculated the complex power absorbed by these two elements. Then I summed that. I said this is the power supplied by the complex power supplied by the source. But if I don't use this approach, I can use the current and multiplied by the voltage approach. Means to get this complex power, I can use S is equal to V times I conjugate. If I know the voltage, if I know the current, I can get the complex power. Okay. So let's end this session here. Please solve further examples from the book Alexander and Sadiq. Okay, let me end this session.